Good evening, everybody. People in the room with us in Hobart, please take your seats. For those of you who are online, I guess you can take whatever position you like. Contrary to what I think it says on your Zoom screen, my name is not Matt Cracknell. I am Mark Duffett, but this is using Matt Cracknell's Zoom account. And welcome to this ASEG Tasmania branch meeting, which we are for the first time also doing as an ASEG webinar, and very pleased and proud to have Richard Lynch speaking to us on passive seismic applications. Just to acknowledge all of the support, and there's a fair bit of sort of ASEG infrastructure and work behind the scenes going on, and that's all supported by our corporate members, who you can hopefully see on the screen now. Thank you very much to all of those companies. And thank you to the various branch sponsors around the place. The Tasmania branch doesn't have a branch sponsor as such, although it occurs to me that we are basically meeting on University of Tasmania premises at no cash cost. And so effectively the University of Tasmania is a de facto sponsor of this branch. So thank you very much to the University of Tasmania. And I would also like to acknowledge the original owners of this land on which we're meeting tonight, as well as being University of Tasmania premises. We're recommending, even though we've got a bit of activity in the chat already, and I'm sort of trying to monitor both streams, but if you could please put questions into the Q&A function on Zoom as we go through, and we'll hopefully have a bit of time at the end to address any questions that may arise. And just also an ad for similar webinars coming up. Jack Muir will be presenting a week from today, also on seismic applications. So look forward to that one. But of course, the big upcoming event is the Australian Exploration Geoscience Conference, which, as you are probably aware by now, has transitioned to being a fully virtual event, and hopefully we can take advantage of the that sort of medium gives us. But there's a lot of online interaction, and so that would be a really good, and it's a really good program. But of course, because we don't have the costs incurred of being an in-person conference, it's now at a substantial discount to the original registration. So I strongly commend that you jump onto that website if you haven't already and get yourself registered for the AEGC in a few weeks' time. And so that's just one of the many member benefits that you can see enumerated there. If you're here or you're online and you're not already an ASEG member, really strongly encourage you to take advantage of one of the best value societies going around. And with that, we'll move on to the benefit that's on offer on this particular evening. Keep in touch with our social media channels, so I see on Twitter particularly. And I'll now hand over to our speaker for this evening, Dr. Richard Lynch, who is relatively recently, I think, arrived in Hobart.
In Hobart. I've been here 7 years ago.
Relatively recently, when you're as old as I am, and from a career in originating in South Africa, but I think operating all over the world in applications of passive seismic, and which he'll tell us a little bit about this evening. I'm really looking forward to it. So thanks very much, Richard, and I'll hand over to you.
Well, thanks very much, Mark. Thanks for the invitation to speak, and thanks everyone for being here. So this evening I'll be talking about ambient noise interferometry, and particularly focused on mineral exploration. It is a method that can be applied on quite a few different areas, but now we'll do the mineral exploration part. Just before I start the talk properly, I'll just mention a few words about Sisprobe, which is the company that I work for. It's a fairly small company in France, in Grenoble. We do have satellite offices in the USA and Australia. I'm the satellite office here. and it's been operating for 4 years. And already it is recognized as the world leader in ambient noise imaging and monitoring for industrial applications like hydrocarbon exploration, extraction, so monitoring of oil and gas fields, mineral exploration, geotechnical, so near surface characterization, monitoring. We do some work in tailings dam, hydro dam kind of space, as well as seismic hazard assessments beneath nuclear power plants, critical chemical factories, things like this. So it's quite a range of activities, but as I said, we'll focus on the mineral exploration part today. So on the mineral exploration side, as we know, the exploration is getting deeper and deeper, more difficult, all the near surface stuff's getting exhausted. The other seismic technique that is used in the mineral exploration world fairly recently is, of course, active reflection seismics, which has been quite successfully used on some projects. But it's quite an expensive technique for use over a wide area. You know, for example, the vibro-sized trucks are quite expensive, big pieces of equipment. Take some planning to get it going. So our technique is similar in some sense in that it uses seismic, but it doesn't need active sources. It's a passive technique, so it uses passive sources. The ambient noise interferometry method itself is it's fairly new in the scheme of things. It's been used for, or become very popular in academic studies in the last decade or so. It essentially accumulates the background energy, which is uncontrolled energy, and creates virtual seismic sources, which you control, and it uses them to study the medium. So it's been used in quite a range of academic studies, volcanology, studying response to earthquakes, earthquake prediction, fault monitoring, etc. And Sisprobe was formed out of the group that essentially founded the method to commercialize this method for industrial applications. And that's the sort of the genesis. So Sisprobe is still headquartered at Melbourne University at AEST, so it has quite a good collaboration with the researchers there. So let's see how we can use ambient seismic energy, noise, to learn something useful about the subsurface. So my talk is organized a little bit like this. We'll talk about interferometry briefly, discuss the origins of seismic noise, the properties of surface waves, which we're going to explore, and then the bulk of the talk will be talking about mineral exploration, giving some examples from Canada, from Australia, from South Africa. I think those two. So interferometry, for those who are not aware, it works by cross-correlating noise seismograms. So if you're recording perfect noise, and I'll explain what perfect means in a second, with two sensors, if you cross-correlate the noise between those two sensors, you recover the Green's function as if one of them was a perfect source, an impulse function there, and you're recording the response of the other sensor. So it's turning the uncontrolled noise. You don't need to know where the noise sources are. You don't need to know the directionality. So as long as the noise is perfect in some sense, you can pull out of that the Green's function between any pair of sensors that you're simultaneously with. So, and in the sense it's recording energy, very weak amounts of energy for a long period, and accumulating them, and then creating a fairly strong virtual source, which we can use to do useful things, imaging, monitoring, etc. So theoretically, we need perfect noise, and the noise would be white stationary noise. It should be isotropically distributed, the noise sources, and at a good distance, not too far, not too close, not within the array. So there should be a sort of a limit on where the noise is coming from. The white and stationary noise, well, it means we need a wide frequency content. So it shouldn't be monochromatic noise. If we've got a pump somewhere, for example, it's not a very good noise source. You get cycle skipping. So you need ideally a white noise source, and you should ideally have it stationary. at the time that we're looking at it, so it should be fairly unchanging. The distribution of the noise sources, well, it shouldn't be, ideally, it shouldn't be one particular place. In this example here, so pretend the world is a one-dimensional world. So you would basically have the impulsive source, the noise source that's uncontrolled. It would be outside the array, so to the left or the right of A and B. And you can see that as it, from that direction, it basically passes A and then passes B sometime later. So if you do a cross-correlation between A and B, you get essentially the travel time between A and B, so related to the distance, the velocity. And if you, so basically, exactly, the cross-correlation gives you an impulse at this expected arrival time. And if you have noise sources at the other side, then basically you would get cross-correlation gives you the same travel time, just a negative, because it's now going from B to A and not A to B. So you can see basically in this world, we would have, you can see that our information that is traveling in a 1D line through B to A contains information about the medium. So even though the noise itself is uncontrolled, just doing the cross-correlation retrieves the information about the medium in that case. So in the 1D example, it's easy to see. You would expect basically, if you've got noise sources all around, you would get this symmetric cross-correlation function. And that would be a good test of that you're getting isotropic sources. In 3D, of course, well, in 2D, let's say you would need sources in a circle. And the sources that are perpendicular to the two sensors would be arriving at the two sensors at the same time. And so that would be very bad. If you only had noise sources that are perpendicular to your array, then you have very limited information between the array. But noise sources all around in a circle, by a stationary phase approximation, you get cancellation. And so you can see that it gives information about the Queen's function between the two. And then, of course, in 3D, you need ideally everything around on a sphere around your sensors. So the isotropic distribution of noise sources is quite a strong condition, but it's not too bad because scattering helps. So basically, even if you've got a single noise source, as long as you've got scatterers around you, they act as secondary sources. So you actually get a nice diffuse field building up from all the scattering. So in this case, the inhomogeneities of the Earth actually really helps us. In theory, then we need sources that are not too close, not too far. We need the scattering all around, so we need isotropic. We need no noise sources in the middle, and we need white noise. So those are theoretically, if you want to extract the true Green's functions, that's the conditions we need for noise. In reality, we don't ever get such perfect noise. Very rarely do we get such perfect noise, but still quite a lot can be done. So this is a nice little example of a magnitude 2.3 earthquake, so a small earthquake that happened to be, so it was recorded by a seismic station at the coast. And that was the recorded waveform, but in this particular case, we happened to have a seismic station, not we, it was a cluster seismic station, but there happened to be one very close to the earthquake. And that's if you take these two stations sometime after the earthquake, and you cross-correlate the noise, that's the cross-correlation, that's the resulting waveform. And if you compare those two, you get very good correlations. So basically the earthquake, which you could, is a small earthquake, so you can treat it as an impulse source. That's effectively like the Green's function between the earthquake source and the sensor. And that is extremely similar to the cross-correlation between the seismic station very close to the epicenter and that seismic station at the coast. So that's sort of a real-life example of this cross-correlation does give very similar things to the Green's function. So where does the noise come from that we're using in exploration? We've got the primary and the secondary microseisms present in our background seismic noise all over the show. And that really comes from the oceanic land interaction. There's two mechanisms for that. So for the primary interaction, it's the quite close to shore effect. It's just the waves and the depth above the sea floor and at particular ratios you get resonances set up. So you get energy being pumped into the landmass from the waves. You get for the secondary microseism, which is stronger, you get an interesting effect of a standing wave setup between reflected waves off the shore and the incident waves, causing standing waves to set up in a particular column of water. And that pumps quite a lot of energy into the landmass. So that, energy that gets pumped in there from the oceanic land interaction spreads all over the landmass. So I'll show you a survey done in central Queensland, which is 1,500 kilometers from the nearest coast. And that wave noise is still really strong and very useful there. You get other sources of seismic noise, which we use, so the cultural noise, which is the high frequency stuff. So that's from car traffic, pumps, fans, in underground mines, human steps. Train noise is a big one that we're using quite a lot. It's quite a good, strong, if you get a cargo train moving around, it's a very heavy thing moving pretty quickly, and it puts quite a lot of seismic energy you can use into the landmass. So the surface waves, we are mainly using surface waves in exploration, mineral exploration. So these are waves that are trapped on the surface of the earth. They're not body waves that are traveling through it. We're mainly using the Rayleigh and Love waves. Rayleigh waves are elliptical. So basically they're present in the longitudinal and the vertical components, so rolling waves. And the Love wave is a transverse wave. So there's some examples, or a little picture basically. So you get the elliptical polarization, you get the horizontal transverse polarization of the Love wave. And that's the two waves we're looking at. These waves are evanescent, so the amplitude decreases exponentially with depth, so that they're trapped close to the surface. But it is important to note that even though they are surface waves, you can penetrate as deep as you like by going super low frequency. So the low frequency waves travel, close to the surface because the wavelength is so long. They're actually sampling tens of kilometers of crust. So it's possible that the high frequency stuff stays close to the surface and the low frequency stuff penetrates deeper. So now if you look at and of course, because of that, they travel at different velocities. So it's a dispersive, So we can take advantage of that to figure out now, okay, what's the different velocity now at different depths? All that information is present in this dispersive nation. So here's some examples now. So this is the Marathon project. It was a EU-funded R&D project. So it's the Marathon project in Canada. It's on the shores of Lake Superior. And the project there was to define, so this was a couple of years back actually, it was to define the geometry of the intrusion contact, identify four localizing structures. So this was sort of the early days where we were looking for ore bodies with ambient noise surface wave tomography methods. And so this was the project objectives and the array that we used there. It's quite a dense array. So it was 1,000 sensors deployed in a sort of a fat line, which I think had 50 meters spacing. So it was quite a dense fat line. And then the 3D part was basically 150 meters spacing. Now, seismic nodes are sort of handheld. They come in a couple of different flavors nowadays. The ones on the right were used in this project. So they were one component sensors. So they've just got the vertical component. And they're quite widely used in the oil and gas industry for reflection seismic surveys. So very commonly available, hundreds of thousands of them used overall. We like to use the 3C nodes because we want to record information about the Love wave too. So the vertical ones are fine for Rayleigh wave. you've got Rayleigh is present on longitudinal and vertical, so you've got information about Rayleigh, but not love. So for love, you need the 3C components. But either way, these nodes are pretty good. They're fairly small, small hole. You dig them, bury them a little bit, so they can be buried under 10 centimeters of soil. You've got a battery, powers them for a month, and you record data internally, and then dig them up, retrieve your data, and that's what you got. And they're not very expensive either, sort of about $1,000 a node, that sort of level. So quite a cool technology that came on the market 10 years ago, 5 years ago. So this is a typical noise spectrum recorded at this marathon project. We've got the dark gray lines on that power spectral density represent the high and low noise models, Peterson's high and low noise models. And you can see our noise is basically somewhere in between, which is sort of what you expect. It coalesces at very high periods, so periods above 10 seconds. That's essentially just instrumental noise. But what is interesting to note is that even though these are 5 Hertz geophones, so they're these little miniature geophones that are used, because they're recorded for a month, it's quite a lot amount of data, you essentially deconvolve the response, and you can recover down to, well, in really good cases, we can recover down to 10 seconds, but usually 3-5 seconds easily. So it's quite great because that means we can use low frequency signals with such convenient geophones. If you look at a spectrogram of the recording periods, at the low periods, the high frequencies, we get this diurnal pattern from human activities, quiet at night and more active in the daytime. And then at long periods, we essentially, the low frequency stuff is coming from bursts of energy from storms. So in this case, it's storms in the North Atlantic that are providing all that wave energy that's then being dumped into the land and we are using. So that actually it's an interesting thing to note how often such things happen, because that starts limiting then the recording period for surveys. In a lot of places, actually, I mean, just a day worth of recording would give enough signal to noise to actually do useful work. But if you need those low frequencies, you need to wait for storms. So it's a little bit like MT. You've got to wait for some of the EM methods. Basically, we've got to wait for lightning storms. So here we need to wait for our oceanic storms. But wait a week pretty much, and you'll catch something like that. Our typical period of recording in surveys is a month when we don't know anything about the area. But with tuning, we've done surveys, repeated surveys in an area, and you can get that down to 1 or 2 weeks deployment time. Looking at, so you can do beamforming on such an array, you can figure out where the different frequencies are coming from. So here we've got the high frequency stuff is actually coming from waves in Lake Superior, as well as actually human activities in Marathon itself. And the very low frequency stuff is coming from the North Atlantic Ocean, from oceanic storms. So now we can do this cross-correlation trick, and between every pair of sensors now. So we've got 1,000 sensors, so there's 1 million cross-correlations, or cross-correlation pairs. And then what we could do is we can stack them by, or plot them by distance away from each other, away from a particular source. So here we've taken a sensor on that side to be the virtual source, and we've plotted the 1,000 cross-correlations at different distances away from it, and that's what you see on the left side there. So what's immediately apparent is that it's asymmetric. So it's not a perfectly recovered Green's function here, because this is asymmetry. You can see and in fact you would even guess that looking at this, because the noise is not coming from all around us. There are preferred directions noises are coming in, and that's what we are seeing here. So most of the noise is coming, let's see, this is negative, so it's coming this direction, and at this particular time. And you can also see that we are getting really good propagation of waves up to even 6 kilometers here. That's the maximum there. And you can even see dispersion with the naked eye there, because you can see right at the end there, you've got high frequency stuff is apparent on the left there. So that is traveling kind of slower, and the low frequency waves are coming in more to the right, because basically they are faster waves. So you can see the dispersion there with the naked eye. And the Rayleigh wave propagation is quite clear here. So we're actually getting it up to 6 kilometers for frequencies below 9 hertz. For the higher frequency stuff, so there's a plot, and you can see it gets very messy later on. So it's propagating quite well up to 4 kilometers. So, now you can play the game of looking at every possible pair. There's a million sort of pair combinations here. And for each one, you start looking at the dispersion curve between the virtual source and the receiver. So we pick then the dispersion curves with an algorithm, and get then pick that dispersion curve with this algorithm. And then we basically build up these maps of velocity in the array for each period. So for each frequency band, we get a map of velocity. And we basically do this for the group velocity maps. This is a very dense array, so we can actually measure the phase velocity directly. And we can then do it sort of independently for the phase velocity maps too. And then what we do is from these group velocity maps, we're able then to basically at particular places, on a regular grid. So you choose a regular grid, and every point on a regular grid, you do a joint inversion of the group and phase velocities of these dispersion curves, and you find a good, well, probabilistically the best velocity model which matches it. So the depth velocity model, a 1D model that we're fitting at a particular place, and then we do this at every single point on that grid, on the 2D grid, and then we glue it all together, and now we have a 3D S-wave velocity model. I should mention it's sensitive mainly to the S-wave, and so yeah, we've played with P trying to extract it, but have found it not very reliable. So we do this, like I said, for every single place, and we then are able to glue it all together, and then build up basically these a proper 3D S-wave velocity model. So where you can take slices of different depths and now start doing interpretation of it. So the Marathon project, for example, it was quite useful in figuring out now where the contacts were between these major ore bodies, or between these major rock units. We were not very successful in this project at finding the ore body itself, because the ore body we were looking for was quite small. So in retrospect, it's too difficult to target. If you're trying to image something which is 100 meters thick at say 1500 meters depth with surface wave methods, you're going to really struggle. And the reason is that basically to get down 1500 meters, to start getting some information about what's going on at 1500 meter depth, you need wavelengths that are like 3 kilometers. And so you've got a Rayleigh criteria problem here. You're not going to be able to resolve things 100 meters wide if you're using 3 kilometer wide wavelengths. So pretty obvious in retrospect. But anyway, chalk it up to experience. But we did find that the method was very good at the major rock units. So if you've got major rock units, the resolution problem is not an issue, and it really gives quite cool information at depth. So I'll show a couple more examples now. So this is a project done maybe last year. I think it finished on probably 2019 in South Africa. So this is in the Northern Cape, near the town of Hotazel, where it's obviously pretty hot most of the time. There's the area we're interested in is sort of that red area there. And we've got noise from 2 sources, 3 main sources. We've got a road there. We've got the town of Hotazel, which you can see is not very big, and we've got a mine to the south. So there are some active noise sources there. The arrays we used, we didn't have 3C geophones available, so we used 1C. So just the vertical components, 120 of them, and it was installed in these two lines, indicated here by the yellow lines there. So it was just two lines, and just to see what we would get out of it. It was also a fairly limited recording time, so 2 weeks. And like I say, we got a lot of energy from the town, the mine, and the road. I should also mention it was a blind inversion, so the mine was playing a little game with us. You know, it's like you do some imaging and stuff, and then we will give you the borehole data, and let's see how it compares. It's kind of a cool game to play. So that's the image that pops out. We've got this sand clay cover unit. It's part of the Kalahari formation on the top. We've got the manganese mineralization, part of the Hotazel formation at the bottom there. The objective was to image the contact, which is quite clear in this case. I mean, it's a very strong contrast between the low and high velocities there. And then there was some borehole data that they gave us. So basically in this section, it's the borehole data. You can see it's not a very deep image. It's only 150 meters deep here. But it matches pretty well. That first contact depth matching is pretty good. You can see there's the contact from the borehole and the seismic borehole. So it's pretty good agreement there. And then the bottom side of it is fair agreement, I would say. So basically at the bottom of the Hotazel formation, you can see it from the passive seismic fairly well in those three places, not so well here. Probably because the Hotazel formation is sort of not very well defined, I guess, there. But pretty good agreement. So that's quite a shallow project, but it was, you know, throw a couple of nodes out for 2 weeks, see what you can do, and it's a fairly good result. This project was done with Anglo-American, Queensland. It's part of, well, the idea was to image the very southern extent of that Mount Isa deposit. And at that area, though, it's quite deeply buried. It's under about 1 kilometer or so of sediment. Nice and hot there. So actually, when we did that initial survey, it was in December, and it was pretty hot. So lots of early morning deployment, and then, you know, sleeping in the middle of the day, and then, you know, early evening sort of stuff too. But anyway, it wasn't too bad. It was actually it was a pretty limited array. We only installed sensors along the road, so it was installed along a 30-kilometer section of the road. So this on a busy slide. So there's now there's been a lot of work done in this area. There's been MT work done, airborne magnetic. They've even done an active seismic reflection along the road. So that's quite a lot of work done. I think a lot of it was done by government, and high size were hired to reprocess the active seismic data. So that's the data that got used here. So basically, I'll show you some sections through it. You know, from even though our sensors were installed, so these are sensors, these little dots here, if you can see them. Even though our sensors were installed pretty much along the road, which is not a very nice 3D, you know, array at all, we were able to still generate a sort of 3D section in this area covered by the road. So, for example, here you do have rays sort of crossing across it, so you can kind of get a section there. Not a very good array for this sort of work. But nonetheless, there is the. Oh, and I should also mention this is another fun one where it was blind. So they, you know, kept the borehole data and all that sort of stuff back, and then we did this comparison afterwards. Yeah, again, we were fairly lucky here. So the Georgina and Eromanga formation, that sedimentary cover on top, you can see that's quite well delimited from the basement underneath, from the faster basement. And And actually it matches the borehole contact very well. Again, now that is about, I think, 850 meter depth. So it's much deeper than that previous one. And so there's like a comparison with the active reflection data too, which is quite fun. So you can see that there's a very strong reflector present in the reflection data, and that matches quite well the interface from the borehole, and matches quite well the interface from the passive seismic. So all of the data agrees quite nicely here, which is pretty cool. And also they've done MT in this place. I believe for some, I'm no geologist, but so I won't try and pretend to explain this, but there is an offset from the MT images from the real layer of about 40 meters apparently. But nonetheless, within this sort of resolution, it matches pretty well. The MT contrast, basically, that's contact, agrees quite well with the seismic data too. So that's pretty cool. Another section. So there's another section here with a borehole in it. Again, the borehole matches quite well with the active seismic and the passive seismic. Passive seismic does something interesting here at the side, sort of rising basically up to a level of, so there's another reflector there, but you know, it's a little bit kind of strange why it does that. But there's no borehole data really to compare against in that place. But anyway, it was a pretty good correlation. We were quite happy with it. Yeah, doing some follow-up work basically. So basically we were able to use ambient noise surface wave tomography to resolve these deep cover contacts, as well as have a peek beneath them. Now it's interesting to note, so these sort of wide area low resolution images are relatively cheap. So we recently did a survey where we got, we used 3 kilometer spacing between nodes. And so it was 5,000 square kilometer survey, and the cost was sort of about 100 or a bit less than 100 Australian per square kilometer. So at that sort of level, it's actually cheaper than aerogravity. It's about a third of the price of, it's about 1% of the price of reflection seismic. So it's one of these methods that I think for these particular applications, you know, cover mapping, the regional geology kind of work, it's a really nice early stage method to be used. But if you try and use it to image very small ore bodies at depth, it's not a very good method to use. So I guess it's all about trying to find the strength and play to that. So just a few concluding remarks. So it seems a little bit like magic to use these background uncontrolled vibrations that are always present there to tell something about what's going on underneath, but it works. We can quickly deploy these self-contained sensor nodes to record the background vibrations over days, weeks, even in environmentally sensitive areas. So we've done lots of work in protected areas where you know, just nodes are hiked in and or even deposited by helicopter actually in some expensive cases. But yeah, so it can be a very low environmental footprint. Currently, we do dig small holes, and so actually, even because they are small holes on a farmer's land, you need to get proper heritage permissions for that. But it can work just as well, actually, with, you know, on the surface covered with big sandbags, in which case there is actually no heritage permission required on farming land, which is interesting. And lastly, it's the latest tool available for mineral exploration geophysicists. Yay. And cover mapping is a particularly good application. So it's inexpensive, relatively easy to collect, and I think it's suitable for regional and prospect scale exploration really early on to sort of aid the gravity data, the magnetic data, etc. So with that, thank you for your attention, and I welcome any questions.
So, fairly early on in the piece, Richard, there was a question that came from Basketova in South Australia. You basically answered it about 1 or 2 slides later about whether the trucks and vehicles 1 or 2 kilometres from the seismic station would be good sources.
Yeah, great sources.
Basically, yes. So, yeah, you covered that one off in the course of the chat. There aren't any others coming in on the chat at the moment. So, are there any other questions from the live audience?
I've got lots of questions.
Great.
Could you comment on issues of both vertical and lateral sensitivity that we covered? Are you better at recovering horizontal interfaces versus vertical interfaces, for instance? And also, the question as to what sort of velocity contrast is required in order to be able to potentially identify something and not really hide it among the smoothing criteria in the inversions.
Okay, so first question, is it better to resolve something that's horizontal or vertical? So unfortunately, I don't have the example here of a diamond pipe, because that's quite a good, nice vertical structure to image. But well, the short answer is it's better to do horizontal stuff. The 1D velocity models then are perfectly valid. And so the inversions are perfectly valid at that place. But we have had places where we've got subvertical structures or subvertical intrusions. So it's quite a big, thick intrusion that is quite well imaged with it. So I think generally, though, it's better to do the horizontal, of course. And then, sorry, the second question again?
The second question was basically a question: if we were, say, to go to a set of drill core and measure P&S wave velocities,
yeah.
At what difference in P&S wave velocity between 2 rocks that we might want to image at the boundary, what difference in S wave velocity is required to be able to image it and not really have the boundary smeared out into the inversion?
Right, yes. Well, the resolution that we are sort of typically resolving here is like 5%, 10% kind of levels. So as long as we've got something that's a bit different to that, then it should be resolved. But of course, it's also about the, if you can have like a big zone basically that is a few percent different from another big zone next to it, you can pretty clearly tell those two apart. But if you've got speckled zones, for example, that are up, down, that gets averaged quite badly. But yeah, I mean, short answer is 5 to 10%.
So, an online question on the chat from Manish Kumar. A month of data could be plenty of time series data to download. How long does it take to process the data from each station?
Good question. So it's yeah, you're exactly right. It's terabytes of data, really a lot of seismic data, because you're sampling the stuff at 250 times a second, on 3 components. So you've got what, 10 bytes per second? No, sorry, 10 bytes per sample, more or less. Times 250, and then you're recording for a whole month. So it's it's hard disks of data that get sent around. And then it's processed on a supercomputer farm. It's really massive. You can see if there's 1,000 sensors. And so the biggest ones we've done are maybe 3,000 sensor kind of surveys. And so you've got, what, 3,000 squared cross correlations that need to be worked out for a month of data each. So really big amounts of data. But fortunately nowadays, you've got, well, supercomputer farms, and you've got AWS, you've got online cloud computing facilities. So you just pay and you can have a lot of computational facility. It's a lot of data to handle. How long it takes to download? Well, it's terabytes.
That might come back into this as you.
I've got a good question about the example of the horizontal formation. There are these vertical artifacts below the sort of key ore horizon. And I just want to get your perspective on, what's causing that, and how you would, if you're trying to interpret this image, this model, how you would, which way should you squint your eyes best in order to resolve that lower contact. The reason I'm asking is because we've seen really similar things in some work that our PhD students is doing here about trying to resolve the tertiary basalt at depth. And he was getting exactly the same vertical artifacts. He was well below the sort of mean that we want?
Well, the short answer is the artifacts. Yeah, it's not a. We see that quite often at the depths of the model, where so you've got rule of thumbs on where you should trust the model and where you shouldn't. You know, you need what's normally about a sixth of the aperture that we can reliably sort of image down to, provided your frequency content of the signals is good. And really, I shouldn't have. We would start a pro imaging map on the depth, so I really shouldn't have shown that image down as deep. So yeah, it's that sort of, you know, overfitting and you know, badly constrained fitting that starts producing that.
Okay, thank you.
The mention of tertiary basalt introduces the next question on the chat from Matt Hutchins quite well, because he asks how many layers can be resolved, and will high velocity above low velocity surfaces be detected?
So how many layers we can resolve? So it's a useful point to point out that, like, so reflective seismics is going for contrast. So any acoustic impedance contrast gives you a nice reflection, and that's what they image. So we're not quite like that. We don't look at the contrast, we look at the velocity model itself. So provided you've got sufficient, the layers are sufficiently big to be resolved. You know, if you've got a layer that's, for example, 10 meters thick at a kilometer depth, you're not going to resolve it. So as long as you've got the layers that are thick enough with that ratio to depth, then there's no, in principle, restriction to layers. There's no problem there. Can you resolve a high above a low? Yeah, sure. We do that all the time in tailing dams, for example. You've got a higher velocity zone, and then you've got the water table at some point, which drops the SO velocity. So you do images like that all the time.
Switching over to the Q&A stream as opposed to the chat, from Andrew Fitzpatrick. A lot of your examples show horizontals continue to be or show bits with active seismic structures deeper than 60 degrees to be able to map. Does passive seismic suffer similar issues with steeply dipping structures? So
no, it can get steeply dipping structures. It's better at horizontal, but we've done a recent project on a salt dome in the US, and actually you can image the side of the salt dome pretty well, and that's quite steeply dipping at that point. So I don't have that picture. That's a nice picture.
I have one more in the chat here, another one from Manish. What would be the optimal / threshold velocity contrast required to map the contact between layers? It's pretty similar to this question.
The optimal is, I don't know, like 100%.
Yeah. So I don't think I've got anything more on the chat. So, but I do have one new person from Victory.
So looking at that imagery with warhole correlations and scale on the side, but how precise were you to the actual depth of the contact in the hole? Like, it was plus or minus a couple of centimeters, a few meters, tens of meters?
I don't know the answer of here, but I know of the Boolean one. There it was sort of a few tens of meters, like 20 meters kind of out. It was pretty close. Here I don't.
On the Boolean example, how to
800 meters. So it was pretty, like, actually I thought we were like lucky there, because I don't expect it to be that good at such depth, but it was.
For a shallow example like the one you have there, if you bench this against just simple HSVR type measurements, you see, because the logistics are even perhaps simpler.
Yeah, sure. So we have actually at Boolean, we ran HSVR there, and yeah, got some results, but weren't really blown away. I mean, it falls naturally. It's like a simple version of our method, and so of course it's easy to collect with our data, our 3C data, but and so we have basically thought, well, we should be using it as an additional constraint, because it's some information in there, and it is a little bit different. It's got amplitude information, which we generally don't have at all. So we're all phase information here. So one of our internal R&D projects is to constrain our inversions using that. But yeah, at Boulia, it wasn't a very amazing result there.
Many people in the Australian exploration industry are using HSVR quite routinely in, say, West Australian environment to map records to depths of 100 to 200 metres. That's why it's directly comparable to what you're showing here.
Yep. Yeah, and actually HSVR, HVSR has got, it's nice advantages because it's one station, you put it there for a relatively short amount of time. It's quite cool like that. But of course, it's got the well-known theoretical uncertainty why it works. But yeah, so it is something that we can pop out of our data. Of course, we are completely overkilling it for that sort of data.
Well, mate, exercise of prerogative, and I might call this the penultimate question. It's something that you mentioned with companies, and you see this through the history of exploration geophysics with relatively new techniques that companies like to do this thing where they just give you the ground and you go and get the data and then they show you all the corroborating stuff afterwards. Basically, is that a good idea? Would you have been able to give them a better result had they given you the borehole, etc., information up front?
Well, I think it's quite a valid thing to do. I mean, to build confidence internally. And so the process that they followed basically is some customers have followed. They've said, right, okay, cool, do the first inversion, which is blind, show us, and then we'll add the other information in, and then do a constrained inversion, and let's see how much it improves, etc. And obviously, the constrained inversion is better. I mean, it's such an underdetermined problem, the inversion issue here, but I don't think it's a bad thing to do. It's quite a fun exercise. It's a little bit dramatic in the company. It's like, right, that's our base case now. Now let's see, take the.
Yeah.
So, no, really bad.
Fair enough. I think I might call this the last question from Victoria.
So back to the Boulia example, when you were telling us the theoretical setup about the noise, I wouldn't have thought having a linear road going through your array where it's bidirectional, and you said noise sources should be out of the array, where you've got the noise going right through it. If it's trucks, because that part of it's pretty remote. Did that affect the outcomes?
So
how do you weed out the noise that was actually in the array as the trucks were going through it?
So actually, the short answer of weeding out the noise as trucks go through is kind of cool, because if you've got 30 days of recording, it tends to average itself out. So you don't really have to do particular data processing techniques to pull it out. In that case, the interest was quite deep targets. They weren't interested in near surface stuff at all. So actually, we didn't use the high frequency information a lot there at all. And actually, to be honest, it's a really desolate region. I mean, it's hardly ever a truck that goes there.
I know.
So it's not a good noise source there. But
so you were using the coastal side.
So it was mainly using kind of coast stuff. Now, even there, you've got you do have surface waves coming from the north part too, but it was, I think, mainly coming from the east. But it was, your array is fairly well arranged to take advantage of that noise. I mean, the noise coming from Gulf and Carpentaria can't really be used if you've got an east-west array anyway. So it was mainly noise used.
The cool thing about that guiding submarkers next to the road is that if a single car drives by, it's in a favorable position 99% of the time, and for a very short period of time, it's between the cars, and we have a favorable space again.
Yeah, that's how you get rid of that recording.
But you don't need to, because 99% of the time it's favorable. So.
Yeah, well, in this case, I mean, it was a 30-kilometre section of road. So even if you were right before the first sensor, you're not going to travel to the following. So we didn't use really the high frequency stuff. But you're exactly right. I mean, if you've got a very dense array and you want to image right underneath the road, then actually roads are pretty good noise sources.
You have to take out the recycling or do they stop you up?
No, they help. So if you've got a lot of them, that's great, but they really are measure zero in the months we're recording. And the energy, if you've got quite strong earthquakes, then that's great. But a lot of this work anyway does, one-bit normalization. You do vicious things to the data. So you're really trying to suppress intermittent, occasional, rare signals and use more the average stuff. So teleseisms are good if there's lots of them, but waves are better.
We haven't quite hit 7 o'clock, so I'm going to contradict myself and slip in one last, really last question that's come from the chat. Another one from Andrew Fitzpatrick. It's a really one. Would doing a passive seismic model provide a better velocity model for active 3D seismic?
Good question. Yes. So we've done projects like this where, particularly the statics in reflections. If you've got quite a complex near surface velocity structure, then when they do the reflection work, it's quite tricky pulling out those statics properly. And so there have been good examples in LA, for example, where ambient noise was used in that very close to surface kind of stuff to get the statics, and then really sharpen the images. And it's quite a dramatic effect. It's pretty cool.